Okay, in part 4, we're looking at the Earth's magnetic field and auroras. So the Earth has a magnetic field, a good strong one, and it extends for hundreds of miles out into space, and it protects our planet. The sun also has a magnetic field, and it extends outward for 100 astronomical units and protects our planet. Now, the auroras are created when particles strike our atmosphere. And we'll talk about how they're focused to the north and south because that's where the magnetic fields terminate. Okay, so anyway, they follow the Earth's magnetic field. We'll be looking at that more. Now, it's not a very strong magnet compared to, your everyday refrigerator magnet, but it is possible. I mean, it is true that some animals do use it for navigation. And of course, people used it for navigation for hundreds, thousands of years. Okay, so the magnetic field of the Earth, kind of the pattern around the Earth looks like it's a giant bar magnet. But of course, it isn't a giant bar magnet within the Earth. But remember we talked earlier about how compasses, the north end is named because it points towards the north geographic pole. Well, that means that since north is attracted to south, the magnetic pole in the geographic north, so like Canada, is actually a south type pole. And we have a north type pole in Antarctica, okay, in the south geographic. So the magnetic field lines around the Earth come out of Antarctica and go in the Arctic. Okay, because we have a north in Antarctica. Okay, now, this is like one of the worst pictures in the book, and it's showing charged particles smacking into our magnetic field lines of the Earth, and they're being deflected or pushed out so that they are not hitting the Earth. A lot of particles don't hit the Earth because of the magnetic field lines. Okay, but occasionally they do hit the Earth, okay, and especially in the north and the south, which is where we get our auroras. Okay, so here's a better picture, okay, of a coronal mass ejection, which is a whole bunch of particles shooting out from the sun. A lot of those particles are alpha particles, which are 2 protons and 2 neutrons, or they are electrons, and they're shooting out of the sun, and they could be damaging when they hit the Earth to living creatures, but a lot of them get deflected and pass around our planet. Okay, or they get caught in these ear-shaped fields, which are called the Van Allen radiation belts. But some of them will spiral along magnetic field lines and come into the north and the south, where the magnetic fields mostly appear to be coming from. Okay, so anyway, so yes, so we do have particles that can be shot out by the sun, and they mostly are deflected around our planet. And the ones that do hit our atmosphere create the beautiful auroras. And so this is not from your book, but this shows how come you get different colors. You get a red or crimson color, well, at the top of the atmosphere, and that's from oxygen atoms from hit by electrons. And then you get nitrogen atoms and oxygen atoms lower down, give you blues and greens. And then you get a pinkish color down even lower from the nitrogen. So it depends on how high they are, which colors you get. Well, and so basically we've got red, greens, and blues. Put those together and they make white, right? So we get reds, greens, blues, combination of those colors, and white looks. So this is called the red crown that you see from space, where that's the highest in the atmosphere. You get the red color. But yes, the aurora often has a lot of green in it. And usually the auroras are circling around the North Pole or the South Pole. So the aurora borealis, borealis means north, the aurora australis, australis refers to the South Pole. And to see an aurora, you usually have to be within about 200 miles. So you can go to space weather sites, or like this is alaska.edu aurora forecast. So what they do is they tell you these pictures are from there. They say, okay, here's where the aurora is. And so that is in Canada. And so to see it, you'd have to drive up probably into Canada to be within 200 miles. But sometimes it comes lower. Okay, so they have lots of these cool charts to show you the activity that's expected. The particles from the sun usually take about 3 days to get to the planet from the sun, so to the Earth. And we know they're coming because we have cameras that are taking pictures of the sun every 10 seconds. And that signal is sent by radio waves, which is faster than the particles. So we know that particles are coming. We have a couple of days to prepare, which is a good idea because those particles can hit and they can overwhelm our electric lines. So a bunch of electrons and protons all of a sudden on our electric lines can actually blow up transformers, which we'll be talking about in the next chapter. And that can take down the whole grid. So that happened in Canada, let's see, about 15 years ago. And they took down millions of people electrical lines, and people were without power for days and days. So anyway, so yes, so the magnetic fields protect us from those particles hitting too often. And so our atmosphere is protected too, because particles can strip our atmosphere. Those particles can cause cancer. Our grid is protected. Our satellites are protected from space particles and by our magnetic field. Now, what is the origin of the Earth's magnetic field? We don't know exactly for sure, but we've got a pretty good idea. We think what's going on is that the Earth has a liquid part to its core. And so it has a solid and a liquid iron part. And we think circulation in the liquid part of the core creates basically electric circuits. So electricity, so electrons and charged particles are moving around in a circular sort of fashion. That's an electromagnet. And so it's currents of electricity in the core that may be creating the magnetic field. Okay, so internal currents of electrically charged particles in the liquid outer core. And one reason we think it's not like a permanent magnet is that it's too hot in the center of the Earth to have a permanent magnet, which is hotter than what's called the Curie temperature. And also because the magnetic field is always changing. So that suggests that it's not a permanent thing. It's something that moves. Now, you're going to watch the movie, The Magnetic Storm, for part of your lab, okay? And so you're going to look at magnetic fields created by computer simulations, okay, as part of that. And they look something like this. And this tangled web is the web of magnetic fields. By the time they get to the surface, they're smoother, but they start off very tangled inside the core of the Earth. And so we have satellites. They're constantly measuring the magnetic field of the Earth, not for science, but because they are looking for submarines. When a submarine, a metal submarine, goes through the magnetic field of the Earth, it creates a change in the magnetic field that can be detected. Just like when you walk through um, a metal detector at the airport, kind of. Okay, so anyway, so people are always measuring. Now, if you'll notice, the red here is indicating that there's a change in nanoteslas, which is a way of measuring magnetic fields. And if you'll notice, there is a triangular shaped one over Bermuda. Scary, huh? But there's also one over Houston, one up here in Canada, big one in California. So yeah, the fact that there's one in Bermuda, that's not what's causing the Bermuda Triangle. It is a little bit out of normal, but it's certainly not unusual enough to cause a lot of commotion. Okay, so here's the North Pole drift too. The North Pole is moving. It moves every year a little bit. Lately, it's been moving rather fast, and new reports seem to say that maybe because humans have actually changed the center of the Earth, well, at least the center of gravity of the Earth, because we've melted so much ice from the polar ice caps, and that water shifts more towards the center, or the equator. And that may actually be causing the North Pole to change its direction. So you can see it was pretty settled for, here's like 100 years down here, and then it started to move. And now it's way up here at the top of Canada. Okay, so this is Canada, so it's moved up like this in this box. However, it isn't actually at the North Geographic Pole. The North Magnetic Pole, which yes is the south, this little white dot here is the actual geographic pole. And it is still 1,000 miles or so away from that. So the North Pole has drifted around before, and explorers had to be aware of that when they had to use the magnetic field to actually locate themselves. And they would have to add what's called the magnetic declination, which is the angle between geographic north and magnetic north. And that depends on where you are on Earth. And so right now, the magnetic North Pole is about 1,500 kilometers, 1,000 miles from the geographic pole. And compasses point to magnetic pole, not geographic, but maps are based on the geographic pole. So what is the angle between magnetic north and true north? And it depends on where you live. We're pretty lucky where we live, because where we live down here, we're only about 2 degrees off, because we're kind of under the alignment of the magnetic north and geographic north. We're under that part of Canada. But what if you live in like Seattle? You would be off by 20 degrees. So if you're lost in the mountains and trying to use a compass and a map, then you would need to be aware that you would have to add or subtract 20 degrees to your measurement for the north. So that declination thing is pretty amazing. But we are lucky where we live. When your compass points north, that's pretty accurate. Like I said, animals do use the magnetic field of the Earth. So monarch butterflies, carrier pigeons, loggerhead turtles, they can detect magnetic fields. Sometimes there's a small bit of like magnetic material close to their brain, and they can actually sense magnetic field lines. So a carrier pigeon sees a map of the sky, and once it's figured out that map, then it can fly back and forth to those locations safely. Loggerhead turtles want to return to the beach where they were born, so they get back to the place where the magnetic fields are the same. And monarch butterflies, of course, have the weirdest life cycle of all. They actually start out in Mexico, go north, lay eggs, they die. The butterflies that emerge keep going north, lay eggs, die. The third generation can get all the way to Canada, so starting in Mexico, end up in Canada. The fourth generation is born bigger and not interested in having babies yet, and they fly all the way back to Mexico. and spend the winter in Mexico. And then the next summer, it all starts again. And so this is one reason that monarch butterflies are so much at risk, because to protect them, you have to protect their whole flight path from Mexico to Canada. And that is one reason to plant milkweed in your yard, because the monarch butterflies have to lay their eggs on the milkweed so that the caterpillars will taste horrible to birds, because milkweed tastes horrible. So anyway, you need lots of flowers around to give them nectar, and milkweed for them to lay their eggs. So anyway, so please plant a garden for the butterflies. Okay. Anyway, one of the weird things about the magnetic field is that it occasionally reverses. Every 200,000 years or so, the magnetic field of the Earth reverses, and the north and the south switch places, not geographically. Okay, Canada will still be in the north, but instead of being a south type magnetic pole in the north, it will reverse to become a north type magnetic pole. And so all our compasses will point in the opposite direction. Now, someday this is going to happen. When it happens, for a while there might be many norths and souths temporarily till the planet has settled down again in its core to just having one north and one south. And in fact, that could take thousands of years. So it could be very exciting, and we are kind of overdue for one, because they should happen every 100 to 200,000 years, and we haven't had one in 700,000 years. So 780 or so thousand years. So we're kind of overdue. So you're going to watch the movie Magnetic Storm, and they're going to talk about how we're overdue for a magnetic field reversal. And we can see these in the rock. This was not mentioned in the movie, but lava that comes out at the Mid-Atlantic Ridge. So this is a whole ridge of volcanoes in the middle of the Atlantic. And lava is pouring out of there, creating a bigger Atlantic Ocean. And as it does that, as it cools down, it locks in the magnetic field that was present. And so what happens is we get stripes of magnetism that cross the Atlantic Ocean. And so we'll have like a north facing magnetic field, then a south, then a north, then a south, then a north, then a south. And so it gets locked in place. And so there's stripes all along the Atlantic Ocean. And so this is what it looks like. This is the Mid-Atlantic Ridge, that white line. Here's Spain over here, and Florida over here, and so on. And you can see all these stripes of magnetism. And the thing is that the Atlantic Ocean was born when Africa was joined to South America, and also the United States was over here. Florida was part of Africa. And so what happened was this ridge started to pour out lava and broke apart Pangaea. Okay, and that is the end of chapter 24. All right.